Today we are going to discuss initial value problems. Initial value problem is a differential equation with subsidiary conditions, some additional conditions. This is, as you see in the example, this is second order differential equation, but it has two additional conditions. If these initial conditions with the unknown function, that is y, and its derivative in y dash, all are given at the same value of the independent variable, so x is equal to pi. The value of unknown variable y is given at the same value of x, so that x is equal to pi. The y and its derivative are given at the same value of the independent variable x. Such subsidiary conditions, these condition, subsidiary additional condition with the differential equation, these additional conditions are called initial condition, and the problem is called initial value problem. For comparison, we can also see the boundary value problem. A differential equation, the boundary value problem is also a differential equation. That is same differential equation, y double prime plus 2y prime is equal to e raised to power x. With the subsidiary conditions, this differential equation and these are the additional conditions on y and its derivative. At more than one point, x is equal to 0, x is equal to 1. Here x is equal to pi, fix one value of x in the subsidiary conditions, but here at least two values of the independent variable. So these conditions are boundary conditions, and these conditions are initial conditions. For the initial conditions, y and its derivatives are given at one value of the independent variable. These conditions are initial conditions, and when y and its derivative are given at more than one point, more than one value of the independent variable, then these conditions are boundary conditions. The problem is called boundary value problem. This is boundary value problem, and this problem is initial value problem. So initial value problem is a differential equation together with initial conditions. This is very useful. In order to solve some physical problems, we use initial conditions with the differential equation and obtain useful results. For example, in this question, discuss the motion of a particle moving in a straight line if it starts from rest at t is equal to 0 and acceleration is equal to a cos t plus b sin t. First of all, we make an understanding of the problem. We have to discuss the motion of the particle, so that we have to find velocity and distance traveled by the particle. We are given acceleration a cos t plus b sin t, and we are given a condition that the particle starts from rest at t is equal to 0. First of all, we start from the given value of acceleration. The acceleration is equal to a cos t plus b sin t. We know that acceleration is d square x divided by dt square. That is equal to a cos t plus b sin t. Now this is the second order differential equation. We have to solve this differential equation. For the solution of this differential equation, we use integration. Integration of the left hand side gives us dx over dt is equal to a integral of cos t dt plus b integral of sin t dt. A integral of cos t is sin t and integral of sin t minus cos t plus a the constant of integration. Now this is dx over dt is velocity. We have obtained with the help of integration the velocity of the particle, but we have a problem for the unknown constant a. This is unknown, so our solution is not final until we do not find the unknown constant a. In order to obtain the unknown constant, we must have an additional condition. The condition is given in the problem that the particle starts from rest at t is equal to 0. So at t is equal to 0, the particle starts from rest, its velocity will be 0. That means when t is equal to 0, dx over dt is equal to 0. We put these two values in this solution. Dx over dt is equal to 0. This is equal to a sin 0 minus b cos 0 plus a the unknown. Sin 0 is 0 and cos 0 is 1 plus a minus b plus a is equal to 0 and a is equal to b. So the velocity is equal to dx over dt is equal to a sin t plus b minus cos t plus the value of a that is equal to b. We have obtained the velocity from this equation, differential equation, with the use of the initial condition. Now we have to find distance traveled at any time. To find the distance traveled, we are again to integrate this differential equation. Now this is first order differential equation, and we integrate this equation to get this result: x is equal to a integral sin t minus b cos t plus b dt, integral of dt. Integral of sin t is minus cos t, integral of cos t is sin t plus bt plus b. B capital is again unknown constant of integration, and we need to find its value. In order to find its value, we use the initial condition that the particle starts from rest at time t is equal to 0. When the particle starts from rest, its distance is initially 0. At time t is equal to 0, x is equal to 0. We put x is equal to 0 and t is equal to 0 in this equation. Cos of 0 is 1, sin of 0 is 0, minus a plus b, b is equal to a. We put the value of b here and we obtain x is equal to minus a cos t minus b sin t plus bt plus a. So we have obtained the velocity and acceleration. This was possible only with the help of the initial condition, and the problem became initial value problem. Unless these conditions are not given, we will not be able to find the solution, a particular solution of this problem of physical interest. Now we continue our practice and we now discuss a very simple initial value problem. This initial value problem is dy over dt is equal to y of 0 is equal to 5. This is the first order differential equation together with initial condition. There is one initial condition, and this is sufficient because the differential equation is first order. If the order of the differential equation is 1, then one initial condition is sufficient to solve it. Now we go to the solution of this differential equation. This is very simple. We use separation of variable technique. We divide left hand side by y and we multiply by dt and obtain right hand side equal to dt. So the problem is separated and in the form dy over y is equal to dt. Now we integrate this equation. Integral dy over y is equal to integral dt. Integral dy over y. This is well-known formula, logarithm of y is equal to t plus logarithm of a. Here the constant of integration is log a, capital. Because on left hand side we have logarithm, so the constant we introduced with logarithm so that we could simplify this expression, and we transfer log of a to left hand side and we get log of y minus log of a is equal to t. Here we use the rule of logarithm. Log y minus log a is equal to log of y divided by a is equal to t. Now we finish logarithm on left hand side. We finish logarithm on left hand side, then its reciprocal is exponential function, that is y over a is equal to e raised to power t, and we multiply by a, y is equal to a e raised to power t. This is equation number 1. We have obtained the solution of the differential equation, but there is problem with the unknown constant a. The initial we have to find this unknown constant a, and we have to use the initial condition. The initial condition is given. This is initial condition, y of 0 is equal to 5. That means when t is equal to 0, y is equal to 5. We put here in equation 1 y is equal to 5 and t is equal to 0, e raised to power 0 is 1, a is equal to 5, and so our solution is y is equal to 5 e raised to power t, and now this is the particular solution of the problem. We now use initial value problem for an interesting physical problem. The problem states that suppose a ball is projected with initial velocity v0 on a smooth horizontal surface. The air resistance is F is equal to minus CV. Find velocity of the ball, where C is constant, V is velocity at any time. For the solution, we use F is equal to minus CV, and from the Newton's second law, F is equal to m dV over dt. Replace F by m dV over dt is equal to minus CV. We separate the variables in this equation and we obtain dv over v is equal to minus c over m dt. Now we integrate this problem v naught to v, dv over v is equal to minus c over m 0 to t dt. This is again the integration rule for is logarithm of v from v naught to v limits is equal to minus c over m t 0 to t limits. We use upper limit first log of v, then minus lower limit log of v naught is equal to minus c over m t. Here again we use the rule of logarithm, log v over v naught is equal to minus c over m t. V over v naught is equal to e raised to power minus c over m t. We multiply this equation by v naught. V is equal to v naught e raised to power minus c by m t. The velocity decreases exponentially. Initial velocity is greater and the final velocity decreases in the exponential form. So with the help of initial conditions we have obtained the result of this problem. Next, this is important problem of everyday life, the simple harmonic motion. Simple harmonic motion, the motion of a particle in which the acceleration is proportional to distance and directed towards the fixed point. Such type of motion is called simple harmonic motion. Consider a particle at point P at distance x from fixed point O and moving with velocity v. Let the particle starts from A at time t is equal to 0. Simple harmonic motion. Consider a particle at point P at distance x from fixed point O and moving with velocity v. Let the particle starts from point A at time t is equal to 0. Then by the definition, the acceleration is proportional to distance. Acceleration is proportional to distance x. So A is equal to minus k x, where k is constant. Because the acceleration is directed toward the fixed point, so acceleration is with negative sign. A is equal to minus kx. This equation is the definition of the simple harmonic motion in mathematical form. Now we solve this equation. Here A is acceleration and we use acceleration is equal to v dv over dx, where v is the velocity at any time or at any position. This is equal to minus kx. We use separation of variables. V dv is equal to minus kx dx, and now we integrate this equation. Integral v dv is equal to minus k integral x dx. Integral of v square divided by 2 is equal to minus k x square by 2 plus a, where a is constant. Now we finish a and multiply this equation by 2, then v square is equal to minus kx square plus b, where b is equal to 2a. We have integrated this equation and we obtained the relation in v, but this is unknown. We have to find this unknown constant b. we will use some initial condition. Initial condition is that the particle starts its motion from the extreme point x is equal to b, so that at the extreme position, when the particle is at x is equal to b at the extreme right, then velocity is equal to 0. We put here v is equal to 0 and x is equal to b plus capital B. We rearrange this one, and b is equal to kb square. So we put the value of b here, and we get this equation like this one: b square is equal to minus kx square plus kb square. Now we rearrange this right hand side: kb square minus kx square, x is common, k is common, b square minus x square, v is equal to plus minus k into b square minus x square under root. This is velocity of the particle at any time. Let us take positive sign. First we take the positive sign, and v is equal to k b square minus x square under root. Here two cases, but we are considering only the positive first. Now we write velocity v dx over dt. This is equal to k under root b square minus x square under root, and we separate the variables. Dx divided by b square minus x square under root is equal to k under root dt. We integrate this equation, differential equation, and this is well known integration: cosine inverse x over b. Cosine inverse x divided by b is equal to k under root t plus c, where c is constant of integration. This is the solution of the differential equation, but the c is unknown. In order to find the value of c, we take t is equal to 0, x is equal to b. Initially, when time t is equal to 0, the particle is at the extreme right position, that is x is equal to b. Say here cos inverse b divided by b is 1, t is 0, so this term becomes 0, plus c. Cos inverse 1 cosine inverse 1 is 0, this is equal to c. So value of c is equal to 0. Value of c is equal to 0, and we get cos inverse x divided by b is equal to k under root t, and x divided by b is equal to cos k under root t. Multiplied with b, we have x is equal to b cos under root k t. This is the motion, this is the distance of the simple harmonic of the particle performing simple harmonic motion at any time t. So this is the equation of motion of the of the particle performing simple harmonic motion. So